Welcome to the Deep Dive. We're here to pull out those key bits of knowledge from some really fascinating sources, aiming for those aha moments,
Exactly.
And today, we're going on a pretty epic journey. We're talking tiny particles all the way up to the whole universe.
And our guide for this is George Gamow's classic 1, 2, 3, Infinity. It's subtitled Facts and Speculations of Science, which sums it up nicely.
Yeah, it really does.
And it's not just like a list of facts. What we want to do is really uncover the principles behind how the universe works.
Right.
Gamow was amazing at making complex stuff, well, simpler, without dumbing it down. He connects numbers, space, matter, life, cosmic evolution. It's all linked.
It's a huge scope, definitely. And we're hoping to show you some connections you might not expect. So let's dive in. We're talking numbers so big, they're almost funny, space getting turned inside out, even the secret lives of genes.
It should give you a whole new way of looking at things, both out there and inside us.
Okay, let's start with something basic, something you use all the time, numbers. But they get weird fast.
They really do.
Gamow kicks off with this anecdote about these two Hungarian aristocrats. They're trying to name the biggest number.
Yeah, I remember this one.
So one thinks really hard and says, 3.
3!
And the other guy, after ages, just gives up. Says, you win.
It sounds totally absurd to us now.
Right, but kind of shows how we even started thinking about quantity. Some ancient tribes literally didn't have words for numbers past maybe 2 or 3. Many, was it? So 5 was just unthinkable.
It's a fascinating contrast, isn't it? Thinking about that versus, say, Archimedes.
Oh, right, the sand reckoner.
Exactly. He tried to calculate the number of sand grains to fill the entire universe. I mean, talk about ambitious.
Even if his universe was smaller than ours.
Much smaller, yeah. But the sheer ingenuity, tackling something that seemed completely incalculable back then, that was a huge leap in thinking.
And if that doesn't stretch your brain, try the problem of a printed line.
Yes, that one's mind-boggling.
Imagine a machine just printing every possible combination of 50 symbols, letters, numbers, punctuation on a line 65 characters long.
Okay.
The number of unique lines is, well, it's staggering, 50 to the power of 65. Even running for billions of years, finding anything meaningful like Shakespeare.
Basically zero chance. Just noise. A cosmic haystack, as you said.
But the really wild part comes with infinity, doesn't it?
Hey, definitely. George Cantor. He showed something that just feels wrong intuitively.
That some infinities are bigger.
Exactly. Bigger or stronger, as he put it. Like the number of points on a line, even a tiny little line segment, is a bigger infinity than all the whole numbers. Or even all the fractions.
How is that even possible?
It involves mapping sets, but yeah, it completely messes with your intuition about infinity just being infinity. He even named them Aleph Null, Aleph 1. We can't even conceive of things for Aleph 3.
Wow. Okay. Speaking of things that mess with intuition, imaginary numbers.
Oh, hi, the square root of -1.
Yeah. Like in school, they just tell you, nope, can't do that. And yet, here it is. Sounds made up.
Well, the early guys thought so too. They called them fictitious or sophistic, but, and this is the key, they started using them to solve problems they couldn't solve otherwise. Like, find 2 numbers that add up to 10, but their product is 40. You need I for that.
Okay, so they're useful even if they seem weird.
Very useful. And later, people like Wessel and Argonne figured out a way to picture them. Multiplying by I is just like rotating something 90 degrees on a graph.
By rotation. That's it.
That's the geometric meaning, yeah. Real numbers on one axis, imaginary on the other. It suddenly makes sense visually.
And Gamow uses that pirate treasure map example, right?
The hidden treasure. Yes, it's brilliant. You have instructions involving an oak, a pine, and a gallows. Walk, turn 90 degrees, walk again.
But the gallows is gone.
Exactly. Seems impossible. But using imaginary numbers, representing that 90-degree turn with I, lets you find the treasure, even without knowing where the gallows was. The I terms cancel out perfectly.
That is genuinely cool. It feels like a magic trick.
It does, and it leads us from, pirate gold to something much bigger.
Einstein.
Einstein's relativity. It turns out these imaginary ideas are crucial for understanding how space and time link up.
Into 4 dimensions. Length, width, height, and time. Okay, I get the first 3. But time, how do you measure that, distance? You can't have, 3 feet in 2 hours, right?
That's the perfect question, and it puzzled physicists too. How do you compare feet and hours?
Yeah.
The answer came from finding a universal speed limit, a fundamental velocity.
The speed of light.
Exactly, about 186,000 miles per second, or 300,000 kilometers per second. It's the conversion factor. It tells you how much distance is equivalent to a certain amount of time.
Okay, so light speed connects space and time units, like an exchange rate.
Precisely. So now you can talk about a four-dimensional distance between events. An event isn't just where, it's where and when.
I like that example Gamow uses, the bank robbery and the plane crash in New York.
Yes. Same day, different locations. In space-time, they're distinct points defined by 4 coordinates, 3 for space, 1 for time. Each event traces a world line through this four-dimensional reality.
And relativity says our usual measurements of distance and time are just perspectives.
Kind of like shadows, yeah. They're projections of this deeper four-dimensional reality. What you measure depends on your motion relative to what you're measuring.
So the faster you go.
Things look shorter in the direction of motion, and even weirder, time slows down for the moving object.
Clocks literally tick slower.
Yes, and not just clocks, everything. Physics, chemistry, biology, all processes slow down equally from the perspective of an outside observer. The person moving fast wouldn't notice anything unusual themselves.
Which leads to that crazy Sirius trip idea.
The twin paradox, essentially.
Fly to Sirius, 9 light years away, near light speed. The round trip takes 18 years Earth time.
Right.
But for the traveler, because time slowed down so much, it could feel like just one day.
Potentially, yes, depending on how close to light speed they get. They'd return to an Earth 18 years older, while they barely aged.
Mind blown. And you definitely can't go faster than light.
Nope. That's where you get the Miss Bright limerick returning yesterday. Light speed is the cosmic speed limit.
Okay, let's shift gears again. Another tough one. Curved space.
Yeah, how do you even picture that from the inside?
Exactly. We're in this space. How can we tell if it's bent?
Gamow's analogy is perfect here. The two-dimensional shadow scientists.
Flatlanders, basically.
Right, living on a surface, they can't see up or down into a third dimension, but they can figure out if their world is flat or curved.
Oh.
By drawing a big triangle. On a flat plane, the angles add up to 180 degrees. Always.
Okay.
But if they live on the surface of a sphere, draw a big enough triangle, and the angles add up to more than 180, they can detect the curve without ever leaving their 2D world.
Ah, I see. So we, in our 3 dimensions, can do something similar.
Exactly. We can measure the angles between straight lines, which, for us, means the paths light travels over vast cosmic distances.
And if they don't add up to 180?
Then space itself is curved.
And Einstein said massive things cause this curvature.
That was his big idea with general relativity. Mass and energy warp spacetime. Think of it like putting a heavy ball on a stretched rubber sheet.
Okay.
So we test this by looking at light from distant stars bending as it passes near the sun, for instance, and it does.
And this applies to the whole universe, too, whether it's curved like a sphere or flat, or maybe like a saddle.
Yes, that's the question of cosmology. Is the universe closed like a sphere, positive curvature, open like a saddle, negative curvature, or flat, zero curvature?
How do we figure that out?
One way is by counting galaxies. How many do we see at different distances? The rate they appear tells us about the geometry of space itself. If the count increases slower than expected for flat space, it suggests positive curvature, a finite, closed universe.
Still working on nailing that down, though, right?
Oh, absolutely. Telescopes like Hubble and Webb are constantly refining those measurements. It's a huge ongoing effort.
Okay, let's completely change scale now. We're going down, down, down into the micro world.
The descending staircase, yeah. Starting with something familiar.
Clam chowder.
Ha, yes. Clearly heterogeneous. You see the bits, clams, potatoes, whatever. Not uniform.
It's a good starting point for thinking about breaking matter down.
It is. And the idea of atoms, these supposedly indivisible bits, goes way back to Democritus in ancient Greece.
But our understanding has changed a lot since then.
Immensely. Alchemists thought maybe fire atoms changed lead to gold. We now know it's about rearranging electrons and nuclei, releasing or absorbing energy. Making iron from ore isn't magic, it's chemistry removing oxygen.
So these atoms,
yeah.
Just how small are they? It's impossible to picture.
Almost impossible, but that oil film experiment Gamow describes gives you a feel for it.
Spreading a tiny drop of oil on water.
Yeah, 1 cubic millimeter covering a whole square meter. It spreads until it's just 1 molecule thick. You can't spread it thinner. That tells you the approximate size of 1 oil molecule. It's incredibly tiny.
Mind-bogglingly small. But can we actually see them?
Well, not with light like we see everyday objects, but indirectly, yes. Molecular beams show how they move, but the real game changer was X-ray crystallography.
Bragg's atomic photography.
Exactly. It's complex, involves bouncing X-rays off crystals, but the end result is basically a picture showing the positions of atoms in a molecule. Like that hexamethylbenzene image Gamow includes, you see the carbon ring. Seeing is believing, right?
Definitely. But then comes the twist.
Yeah.
Atoms aren't solid little balls.
Not at all. They're mostly empty space with, as Gamow puts it, complex mechanisms inside.
So what's inside?
Well, the first models were sort of like plum pudding or a watermelon.
J.J. Thomson's idea.
Yeah, a blob of positive charge with little negative electrons embedded in it.
Sounds plausible.
It did until Rutherford. Around 1911, he did this famous experiment shooting alpha particles, which are like tiny bullets at thin gold foil.
And what happened?
Most went straight through, as expected if the atom was mostly empty or soft. But some bounced back. It was like, he said, firing a cannonball at tissue paper and having it bounce back at you.
Whoa. What did that mean?
It meant the positive charge and almost all the mass had to be crammed into an incredibly tiny, dense spot in the center of the nucleus, the rest of the atom, empty space with electrons orbiting far away. A total rewrite of the atomic model.
The planetary model?
Yeah.
Electrons orbiting like planets.
Right. But that model had a huge problem too, a classical disaster.
What was it?
According to classical physics, an orbiting electron should constantly radiate energy.
Okay.
Which means it should lose energy and spiral into the nucleus in like a fraction of a second. Poof. Atoms shouldn't be stable. Matter shouldn't exist.
Clearly that doesn't happen.
Yeah.
So classical physics breaks down here.
Completely breaks down at the atomic scale. This crisis forced the development of a whole new physics, quantum mechanics.
Quantum physics, where things get really weird.
They do. Forget neat, precise orbits. Quantum mechanics says you can't know exactly where an electron is and where it's going. It exists more like a probability cloud, a region where it's likely to be found.
A cloud, not a point.
More like a wave spread out in space. It's this wave-particle duality thing. Just like light acts as both waves and particles, so do electrons and even whole atoms.
Atoms behave like waves.
Yep. Experiments actually showed atoms diffracting, bending around obstacles just like light waves do. It confirms this fundamental weirdness. Particles are waves, waves are particles.
Okay, deep breath. So inside the nucleus, what's there?
Protons, which have positive charge, and neutrons, which have no charge but similar mass, collectively called nucleons.
And this relates back to Prout's idea, that everything's made of hydrogen.
Kind of. Prout was sort of right in spirit, but wrong in detail. The discovery of isotopes elements with the same number of protons but different numbers of neutrons explained why atomic weights weren't simple multiples of hydrogen. But the basic idea that things are built from fundamental blocks held up.
So protons, neutrons, electrons. That's it.
Pretty much the core building blocks of ordinary matter. You can write recipes for anything water, salt, TNT, just by specifying the number of protons, neutrons, and electrons needed.
Plus that other particle, the neutrino.
Ah, the neutrino. That came about to solve another puzzle, the recoil problem in certain types of radioactive decay. Energy and momentum seem to be missing.
Like a gun firing without a kick.
Exactly. So Wolfgang Pauli hypothesized this tiny, chargeless, almost massless particle was carrying away the missing energy and momentum, the neutrino. Incredibly hard to detect because they barely interact with anything.
So nucleons, electrons, neutrinos, those are the fundamental ingredients.
As far as stable matter goes, they seem to be the bedrock, yes. Though physicists are always looking deeper.
And what about that idea of inverted matter?
Antimatter. Yeah, nuclei made of negative protons, antiprotons, orbited by positive electrons, positrons. Theoretically, it should behave identically to normal matter.
Until
it meets normal matter. Then, annihilation. A huge burst of energy. Pure EMC simmer.
Wild. And we actually make this stuff.
Tiny amounts in particle accelerators, which are these amazing tools scientists built to probe the nucleus.
Like cloud chambers, cyclotrons?
Electrostatic generators, linear accelerators, yeah. All designed to smash particles together at high speeds and see what happens, which led directly to understanding nuclear fission.
Splitting the atom.
Splitting heavy nuclei like uranium. And the key discovery was that fission releases more neutrons.
Which can then cause more fissions.
A chain reaction. Suddenly you have a way to release the immense energy locked inside the nucleus on a large scale. Nuclear power, but also, unfortunately, nuclear weapons.
The energy potential is huge, though.
Yeah. Astronomical. Gamow mentions that the uranium and thorium available could power the world for thousands of years. Tapping into the nucleus changed everything.
Okay, let's pivot from the purely physical to, well, life, the mysterious phenomenon of life.
Another huge leap in scale and complexity. We go from atoms and molecules to cells, tissues, organisms.
And Gamow brings up viruses here, right, as a kind of bridge.
Exactly. Viruses are weird. They're on the edge. Are they alive? Are they just complex chemicals? They blur the line.
Like the tobacco mosaic virus example. It's tiny, just a few million atoms.
You can crystallize it, like salt or sugar, store it in a bottle indefinitely, seems totally non-living, put it back in a tobacco leaf, and boom, it starts replicating, making copies of itself, causing disease. It behaves like a living thing again. It's astounding.
How does that even work?
Well, experiments showed you could break a virus down into its parts, basically a core of ribonucleic acid, RNA, and an outer protein coat. Neither part is alive on its own. But mix them back together in a test tube. They spontaneously self-assemble back into active infectious viruses.
Wow, so life at that level is about molecular self-organization.
That's what it suggests. The blueprint is in the molecules themselves, which leads us to genes and chromosomes.
The carriers of heredity, found in the cell nucleus.
Right, those fiber-like chromosomes. We get one set from each parent. They hold the instructions, including things like the X and Y chromosomes that determine sex.
And the genes are parts of the chromosomes.
Yes, genes are specific segments along the chromosome. Gamow uses that great analogy, like a charm bracelet made of nucleic acid with different chemical groups or pendants hanging off it.
And each pendant determines a trait, like eye color.
That's the basic idea. Each gene is a sequence that codes for something specific, and they're complex molecules themselves, made of maybe 1 million atoms each.
And changes, mutations happen at this level.
Yes. And crucially, mutations are often jump-like. They're not usually gradual blends. It's more like one of those pendants on the charm bracelet suddenly changing or swapping position.
An isomeric transformation.
Right. A sudden chemical rearrangement within the gene molecule. That's why you get distinct variations, like sudden short wings in fruit flies or conditions like color blindness. It's an all-or-nothing change at the molecular level.
It really brings biology down to chemistry and physics.
It absolutely does. Life emerges from the complex interactions of these non-living molecules, governed by the same fundamental laws.
Okay, let's zoom all the way back out. Microcosmos time. The big picture.
Back to the stars and galaxies. And our understanding of our place in it all has certainly evolved.
Hugely. From flat Earth ideas, thinking people on the other side would fall off.
The Antipodes problem. Yeah, hard to grasp intuitively back then.
To Aristotle, figuring out the Earth is a sphere. It's a story of expanding horizons.
And a key tool for that expansion was parallax.
Measuring distance using angles.
Exactly. Like using your two eyes to judge depth. Astronomers use the Earth's diameter as a baseline to measure the moon's distance. Then, they use the Earth's orbit around the sun as a much larger baseline to measure the distance to nearby stars.
Like Alpha Centauri, about 4.3 light years away.
Right, that's the first step in mapping the cosmos.
And the scale is just immense. Billions of stars in our galaxy alone.
The Milky Way. Gamow calls it a giant beehive of maybe 40 billion stars. And our sun isn't even near the center, we're out towards the edge.
And we figured out the whole galaxy is rotating.
Yeah, Genor did brilliant work on that. By observing how stars seem to move relative to us, accounting for our own motion, he showed the entire disk is spinning. It's like how Copernicus explained planets seeming to loop. It's about perspective.
And our galaxy isn't the only one out there.
Far from it. Those spiral nebulae people saw in telescopes, turns out they were other galaxies. Island universes in their own right.
Like Andromeda.
Andromeda, our nearest large neighbor, about 1.7 million light years away, looks similar to our own Milky Way.
So how do we measure distances that far? Parallax must be too small.
Way too small. We needed new standard candles. Things whose true brightness we could figure out.
Cepheid variable stars.
Exactly. Henrietta Leavitt discovered that the pulsation period of these Cepheided stars is directly linked to their actual luminosity. Measure the period, know the true brightness, compare it to apparent brightness, calculate the distance.
Like using a light bulb of known wattage.
Precisely. This let Hubble and others measure distances to galaxies millions, even billions of light years away. It opened up the observable universe.
And mapping those galaxies brought us back to the shape of space question.
Right back to it. Counting galaxies at different distances, like we discussed. Does the count fall off, suggesting positive curvature in a finite universe? The data leans that way, but it's still an active area of research.
Okay, final stretch. The evolution of everything. Earth, stars, the universe itself.
Where did it all come from? How old is it? Big questions.
We know the Earth is old. Molten interior, radioactive dating.
Yeah, radioactive clocks in rocks using uranium, potassium, rubidium decay consistently point to the Earth's crust being about 4.5 to 5 billion years old.
And the solar system itself, how did it form?
Well, the old Kant-Laplace nebular hypothesis, a spinning cloud flattening, rings forming planets, had issues. Then came the collision theory, another star hitting the sun.
But that had problems too, right?
It did. Hard to explain the planet's nearly circular orbits. So science circled back, in a way. With new understanding of interstellar dust and gas, a revised nebular idea, like Weizsäcker's theory, became dominant again.
Dust bunnies, basically.
Kind of. Tiny dust grains sticking together, growing into planetesimals, then planets, all within a rotating disk around the young sun. It fits the evidence much better now.
And the sun itself. How does it keep burning for billions of years?
Thermonuclear fusion in the core, insanely high temperatures like 20 million degrees Celsius, primarily converting hydrogen into helium.
Gamow mentions the carbon-nitrogen cycle.
Yes, one of the main processes in stars like our sun. It fuses hydrogen using carbon and nitrogen as catalysts. It burns through hundreds of millions of tons of hydrogen every second.
And yet it lasts billions of years. That's how much hydrogen there is.
Exactly. But eventually the fuel runs low.
What happens then?
For stars like the sun, the core contracts and heats up, the outer layers expand, it becomes a red giant, and eventually sheds its outer layers, leaving behind a dense core.
A white dwarf.
A white dwarf. Small, maybe Earth-sized, but incredibly dense. A teaspoon would weigh tons. That's the quiet end for most stars.
Not all stars go quietly.
No, indeed. Some go out with a bang. Novae, and especially supernovae.
Titanic convulsions.
That's a good way to put it. A supernova can briefly outshine its entire galaxy. It's the explosive death of a massive star.
What causes that explosion?
The current understanding involves core collapse. When a massive star runs out of fuel, gravity wins. The core collapses catastrophically fast. This triggers reactions that produce a flood of neutrinos again. They stream out, carrying away immense energy very efficiently, which accelerates the collapse. Then there's a massive rebound shockwave that blows the star apart,
leaving behind amazing things like the Crab Nebula.
Remnants filled with heavy elements forged in the explosion, elements essential for planets and life. We are literally stardust.
So pulling it all together, the universe isn't static, it evolved, it had a beginning.
All the evidence points that way. A beginning, billions of years ago. A state of incredible density and temperature where even heavy elements were cooked.
The Big Bang, essentially.
Call it that, yes. An initial expansion from a super dense state. And the crucial thing is, it's still expanding. Galaxies are rushing away from each other.
Will it expand forever? Or collapse back?
That depends on the overall density and curvature. But based on current measurements of how fast things are moving apart and the amount of matter and energy we can detect,
what's the verdict?
The data currently suggests it will keep expanding forever. It seems the expansion is even accelerating. It's heading towards, well, infinity with no sign of turning back, though, there's always uncertainty in these cosmic measurements.
Wow, what a journey. From 3 being the biggest number, to electrons acting like waves, to the universe expanding forever.
It really covers the whole spectrum, doesn't it? From the tiniest quantum jitters to the grand cosmic narrative. Gamow's book really ties it all together beautifully.
It shows how science connects everything. Numbers, physics, chemistry, biology, astronomy. It's all one unfolding story.
It is, and it's a story we're still writing, still figuring out. Every discovery adds a little more detail, refines the picture. It's the power of inquiry.
So, the final thought for you, listening. If our universe really does operate on these fundamental mathematical laws, from how air molecules bounce around to how galaxies spread out, and if even our own genetic code is like that charm bracelet of atoms dictating life, what comes next? What other infinities, what deeper layers of reality are waiting for us to uncover? Both, out there in the cosmos and maybe even hidden within ourselves as science keeps pushing the boundaries of what we know.
That's the question, isn't it? What's beyond the horizon?
Something to think about. Keep exploring. Keep asking questions. Thanks for joining us on this deep dive.